The question is the following. We studied the inverse problem of differentiation, i.e., given a function little f, we want to find a function capital F such that capital F derivative is given by little fx. Okay. So this is inverse operation of differentiation. Then what we do is we rewrite the differentiation table backwards so that we get an antiderivative. Okay, antiderivative. So this table is very important. Then you should write down, then you should know every item in this table. Okay. Okay. The idea for we define antiderivative, okay? Then antiderivative and differentiation, they are inverse operations. Inverse operations. If we have certain rule in differentiation, like a chain rule, product rule, etc., then by the inverse operation, then we can push this kind of rule by this inverse operation to get a rule in antiderivative. Okay, so chain rule corresponds to a rule called substitution rule. Product rule corresponds to a rule called integration by parts, etc. So linear property in differentiation will correspond to different linear property in antiderivative. Okay, we introduced the notation for antiderivative here. Yeah, this notation. This notation. Okay. This notation. Okay. This notation is defined as antiderivative. Remember, antiderivative is only determined up to a constant. Antiderivative is determined only up to a constant because constant derivative vanishes. If you add any constant c, the derivative does not change. Okay, the derivative is only determined up to constant. So as we choose a different constant, then we get a different antiderivative. So as actually the constant, we choose different kind of constants, then we get a family of antiderivatives. So this kind of family of antiderivatives, we use a notation, we use this notation to define, and we use this notation as a family of antiderivatives, and we call it indefinite integral of f. Okay, indefinite integral of f. This is what we call an indefinite integral. So here dx is called differential. This integral symbol, this integral symbol looks like an S. Okay, it's actually an elongated S. Okay, this comes from the letter S. Okay, comes from the letter S. Elongated letter S. Okay. Here S means sum. Here S means sum. In next chapter, you will see why this thing is actually a sum. Okay. Okay, now. Okay, remember, let me explain why we have a dx here. Okay. If you play around with the logic, derivative of antiderivative, derivative of antiderivative will be the original function itself, i.e., if we let a capital Fx be the antiderivative of little f, then by definition, we take the derivative of capital F, then we should get a little f. Now, if you substitute this capital F by this indefinite integral, okay, indefinite integral, then you see what we get is this, d over dx, integral fx dx. Now, here the relation of this fx and the differential dx is multiplication. Now, if you formally think dx cancel dx, okay, formally saying dx cancel dx. Then what you get is, then is the next step, what you get is, so this, what you get is d, this thing, fx, okay? Then d cancels this integral, okay? They are inverse operation. This d means differentiation. This integral means antiderivative. They are inverse operation. Remember, they are inverse operation. Like multiplication cancel division, addition cancel subtraction. They are inverse operation. So here, differentiation and integration, they cancel each other. So they cancel each other. So they actually will get a little fx, okay? So this notation is actually well designed, very logical, this notation, okay? Now, if we first do differentiation and then do antiderivative, okay? If we first differentiate, take derivative and then we take antiderivative, so suppose we take little fx to be capital F derivative, Then if we take an antiderivative of this little f, now actually we have a candidate for antiderivative, i.e. capital F, okay, capital F. Remember, antiderivative is only determined after constant, so we get this to be capital F plus constant c. Now if you unravel the definition, substitute the little f by capital F derivative, d capital F over dx, multiply dx. Now you see, formally you can cancel dx with dx, okay? So what do we get is actually this. What do we get is this. Then we get an integral df, okay? Integral df. Then this integral and d, they cancel each other. Integral and d, they cancel each other, okay? So integral and d, they cancel each other. So d and d and this integral, they cancel each other, okay? They cancel each other if they there's nothing in between them, okay? So actually they cancel each other up to a constant. So we get a capital F plus c, okay? So this these two equations means d and integral, they cancel each other, okay, up to a constant, okay? They are not exactly inverse. They are inverse operation up to a constant c, okay, up to a constant c. Okay. I think we do some examples of this antiderivatives. All right, now let's do some antiderivative examples. Now, right now, the only tool that we have to do antiderivative is antiderivative table, okay, antiderivative table. Now, example. Okay, let's see this example. Fx is x to the power 20 plus 4 times x power 10 plus 8. Find antiderivative. Find antiderivative. Find antiderivative of little f. Okay, so little then the first step, we substitute the little f by the explicit expression. Okay, then we use linear property. We can distribute. Okay, distribute linear property. Okay, you distribute linear property. Now any constant you can factor out. Okay, any constant you can factor out. Now this 8 you can also factor out. Then you get a 1 multiply dx. Okay. Now and then, so what we did is you use linear property. Exactly like what we did, use the linear property for derivative. Okay. Then we check antiderivative. We use antiderivative. X to the power 20. X to the power 20. Then this is a power of x. Then we use power rule. When we do derivative, the exponent decreases by 1. And then we factor out the exponent, okay? Factor the exponent, and then the exponent decreases by 1. When we do antiderivative, it's the inverse, okay? Inverse. Then we do not decrease the degree anymore. Then we increase, okay? Increase. So we increase power, increase the exponent by 1. And then divide 20 plus 1, okay? And then for x power 10, we increase the power 10 plus 1, increase the exponent by 1, then divide the exponent by 1, then divide the exponent, then multiply the constant coefficients. Now, antiderivative of 1, we get x, okay? So this is the 8x, okay, 8x. Once we are done for every term, then we write a constant c at the end, okay? So this will be if you so this will be x to 21 power over 21 plus if you do cancellation, there's no cancellation here, plus 8x plus c. Okay, now you can use this linear property and the power rule. You can find any derivative of any polynomial. Okay, any polynomial. Okay, more example. Okay, let's see this example. Fx is 6 square root of x minus let's see 6 root of x. Okay, so this is the power of x. We use power rule. Okay, so if you write anything as 6 times x, square root means 1/2 power. Okay, so this is x to the power 1 over 6. Now to find antiderivative, what do we do is we use power rule. Okay, we use power rule. Okay, if you distribute, so this will be factor out the constant 6. Okay. Then the exponent increase by 1 and then divide. Okay, then the exponent increase by 1 and then divide. So x 1/2 power, so f 1/2 plus 1, then divide 1/2 plus 1, divide the exponent. Then x to the power 1 over 6 plus 1 over 1 over 6 plus 1. Okay, then what we get is 6 times x to the power 3 over 2. Now if you divide this number, divide by 3 over 2, then you flip the denominator with numerator. Okay, flip the denominator with numerator. So you multiply 2 over 3. Now this x negative here. X to the power 7 over 6. Then you divide 7 over 6. You multiply 6 over 7. Okay. Then this you get 4x the thing minus, oh, don't forget constant c, sorry. Okay, then you're done. Okay, then you're done. Example. Fx is 1 over twice square root of x. Okay, fine. It's antiderivative. Now this is we use antiderivative. Okay, the only tool right now to find antiderivative is antiderivative. Okay, antiderivative. Okay, what we do is you check. So fx is 1 over twice square root of x. You write as the thing as 1 over x to the power 1/2. This is the 1/2 times x to the power negative 1/2. Okay, negative 1/2. Then we use antiderivative. This is 1/2 x to the power negative 1/2 dx. If you factor this 1/2, then what you do is we increase exponent by 1. Okay, don't forget this constant 1/2. Increase power by 1, then divide. Once we're done, we put some c. Now finally, you see this is 1/2 times x to the power 1/2 divided by 1/2 plus c. 1/2 cancel 1/2, so this is actually x 1/2 power plus c, i.e. this is square root of x plus c. Okay. Okay, more examples. Example. How should we do this example? Now this example is a fraction, is a quotient. Right now, the only tool we have right now is antiderivative table. The thing is, if a function is not in the antiderivative table, then we will try to do algebra such that we can write it as linear combinations of functions in the antiderivative table. Okay, so for this quotient, we will try to split the terms such that we have such that every term that we get, we can deal with it by antiderivative table. Okay, so the idea is we split factors. Split terms. Okay, so this is x plus 1 plus 1 over x. Now each term is a power of x. Okay, each term is a power of x. Then we can use power rule. Okay. Then fx dx antiderivative is x plus 1 plus 1 over x dx. Okay. Now distribute x dx plus 1 dx. 1 times dx you can write as simply as, okay, so here 1 times dx you can simply write as dx. Okay, 1 times anything is itself. Okay, then you see d and integral, they cancel each other, so they cancel each other, d and integral, they cancel each other, so what we get is actually x. But here remember, it's only up to constant, determine up to constant. When we do antiderivative, it's only determined up to constant. Okay, so this x squared will be x antiderivative will be 1/2 x squared power rule. Now x derivative is 1 derivative is x. 1 over x has antiderivative ln up to value of x plus c. Once we're done, please count c. Okay, remember, be a little careful. So if you check this function, check example. 1 over x is antiderivative is ln up value of x, not ln x. Okay, so if you let fx be ln up value of x, and it has two pieces. Okay, here x is non-zero. It's undefined when x is 0. So when x is positive, so this will be ln x if x becomes positive. If x is negative, then this will be ln negative x. Okay, if you check, now if x greater than 0, then f derivative is ln x derivative, which is 1 over x. Okay, if x less than 0, f derivative x is ln negative x derivative. Okay, by logarithmic differentiation, what we do is we flip the input of ln negative x. Okay, then by chain rule, the inner function is negative x, so we apply chain rule. So we need negative x derivative again. So this x negative x derivative get negative 1, negative x over negative x. So this is the 1 over x again. So even if whenever x is positive or negative, then we see the function derivative is 1 over x. Okay, so we have ln absolute value of x derivative is 1 over x. Okay, so here x can be negative, x can be positive. Okay. Okay. More examples. More examples. H theta is sine theta over cosine squared of theta. Okay. Now, if a function is not in the antiderivative table, what we do right now is we use algebra, try to simplify, try to construct so that we get a linear combinations of functions that are in the antiderivative table. Okay. So for this one, what we do is if you check antiderivative of trig functions, you see sine derivative is cosine theta. Okay, then you get antiderivative cosine theta is sine theta plus c. Remember, we also have remember cosine. Just write down cosine derivative. We get negative sine times the derivative. We get a secant squared. Okay, so here we have some squared. So we should consider secant derivative. What is secant derivative? Remember, secant derivative is secant tangent theta. Okay, so what we do is we use antiderivative table. Then if we use antiderivative table, then we get a secant tangent antiderivative d theta. This will be secant theta plus constant c. Okay, plus constant c. So this we write it as, so this sine theta over cosine theta squared is not in the antiderivative table at the first sight, but however we can try to algebra, write cosine theta as cosine theta times cosine theta, right, in this manner. Okay, so the denominator is cosine theta times cosine theta, so we get a cosine theta squared. So then we do algebra, sine theta over cosine theta. By definition, this will be tangent theta. 1 over cosine, by definition, this will be secant theta. Okay, so then h theta antiderivative will be tangent theta secant theta d theta. Now you check, this is exactly in the antiderivative table. Okay, in the antiderivative table, secant tangent theta d theta. Okay, multiplication is commutative. You can switch in any order. Okay, so this we get this will be the antiderivative to be secant theta plus constant c. Okay, then we are done. Then we are done. Okay. Okay, more examples. More examples. Example. Okay, we do this. F derivative of t equals 2 cosine t plus secant of squared t, secant t squared. Here, t is from negative power 2 to power 2. And f power 3 is 4. Find ft. Find f. Okay, from f derivative, we need to solve the function f. Okay, from f derivative to solve f. What we do is we use antiderivative table. Okay, so use antiderivative. So ft is from its antiderivative table. So ft is determined up to constant by its antiderivative. Okay, so here we actually we abuse notation a little bit. We actually abuse our notation. So the right side is actually a family of antiderivatives. Okay, to be more precise, the right side is a family of antiderivatives. However, the left side is only a function, one function. So here there's slightly abuse of notation. You need to be careful a little bit. Then, so this will be twice cosine of t plus secant square of t dt. And then we can use linear property so that we can distribute the functions, constant 2, okay, the coefficients 2, you can factor out, okay? So you get 2 cosine of t dt plus secant squared of t dt. Okay, then we use antiderivative table. Cosine antiderivative. What is cosine antiderivative? We just write down, okay? Cosine antiderivative sine, okay? The variable here is t. Secant square antiderivative, remember? What is secant square antiderivative? Secant square antiderivative is tangent, okay? Tangent. Check antiderivative table or the derivative table. Once we are done, we plus constant c. Now, actually, if we have more information of the function f, then we can actually determine the constant c. Here we have the function value, special value at pi over 3. Then we plug in t by pi over 3. Okay, so plug in t by pi over 3. So f pi over 3, plug in the special value, which we get twice sine pi over 3 plus tangent pi over 3 plus c. The thing is 4. Now, what is your special value of sine? Okay, special value of trig function. Then we get twice sine pi over 3. What do we get? Sine pi over 3. What do we get is root 3 over 2. Okay, root 3 over 2. How about tangent of pi over 3? Tangent pi over 3 is root 3. Okay, plus constant c is 4. So you see, this should be twice times 1/2 root 3. Then we get root 3 plus root 3 plus c is 4. So this is actually twice root 3 plus c is 4. So c is 4 minus twice root 3. So then we can write down the function as f of t is twice sine t plus tangent t, now plus constant c. The c we already know is 4 minus twice root 3. Okay, then we are done. Okay. Okay, every time we do antiderivative, we have one undetermined constant. Okay. If we do twice antiderivative, then we have two undetermined constants. Okay. For instance, okay, example. If we know second derivative, f double derivative, second derivative, which will be 6x plus 12x squared. Find fx. Okay, so from second derivative, we do antiderivative, so we get first derivative, and then we do derivative again, so that we recover the function f. So f first derivative is we do antiderivative one time, Okay. Derivative or second derivative is first derivative. Okay. So this will be 6x plus 12x squared dx. Okay, distribute. Or you use directly power. Okay. So increase. So this is 6. If you write more steps, 6x. So distribute 6x dx plus 12 x squared dx. And then you factor out this power 6, this constant, the coefficient 6. Factor out the coefficient 12. Then you get this will be power 1 increase power by 1. So we get power 2. And then divide. So power 2 increase power by 1. We get 3. And then divide by 3. Then multiply the coefficient 12. Once we are done, we write constant cy. So excuse me. So we get 6 over 3, 6 over 2. We get a 3x squared. 12 over 3. So we get a 4 plus c1. So we get f first derivative. Then we do antiderivative again. What happened? Okay, so this will be 3x squared plus 4x cubed plus cy antiderivative dx. Okay, then we distribute. Then we get a 3x squared dx plus factor out the coefficients. Now cy, you can also factor out cy, okay, as dx. If you factor the cy, you get 1. Antiderivative is c1x. Now 4x cubed. So the x increase power by 1, then divide. X squared increase power by 1, so we get x cubed over 3. Once you are done for every antiderivative, you write constant c. At the end, c2. So this will be x cubed plus x power 4 plus c1 x plus c2. So here you see we have 2 constants, okay, 2 undetermined constants, c1 and c2. Okay. Okay, to determine c1 and c2, we need 2 conditions. In general, we need 2 conditions. Okay, so let's see this example. F second derivative. F second derivative x is this example. 24x squared plus 2x plus 10. Okay. We know f1 function value at 1 is 5. F derivative at 1 is -3. So we want to find f. We need to find f. Find fx. Okay. So from second derivative, we first find the first derivative, f prime, by antiderivative. Okay. So by antiderivative, f derivative is antiderivative of second derivative. Okay. And then we substitute the explicit expression. Dx. Then this will be, we factor out the terms. This is 24x squared dx plus 2x dx plus 10 dx. And then so this is distribution property, linear property. Distribution, linear property. So you can distribute. And then we factor out the constant 24. We factor out the coefficients. Okay, use antiderivative table. Now x squared over 2. Now this d cancels this integral directly, so this is x. Once we're done, we write the constant c at the end. Okay, so this, if you simplify this, so this will be 8x cubed plus x squared plus 10x plus c. Now to determine the constant c, so we need to use information about f or f prime. So f, so we know the value. Remember, the value is given. F derivative at 1 is given by -3. Look at the first line. Look at the first line. The first line. Okay, the first line. F derivative at 1. So this is f derivative x. Now we know f derivative 1 is -3 is given. Then we plug in. So this we get 8 x cubed plus x squared plus 10x plus c. Then we plug in f derivative at 1. F derivative at 1. F derivative at 1. Plug in x. So f derivative at 1. So here this is sorry. Yeah, this is right. F derivative at 1 is -3. F1 is 5. Okay, f derivative at 1 is -3. So we plug in x derivative. Plug in x by 1. Then what we get, the thing is, this is 8 plus 1 plus 10, so it's 19. 19 plus c. Now we know this is actually is given also by -3. -3, okay, -3. So we can get, so we can solve for c. C should be -3 minus 19. So we get a -22, okay, -22. So f derivative x, we solved f derivative x, which will be 8. Substitute the c by -22. Minus 22. Then from first derivative, we do antiderivative again. So fx is antiderivative of little f of f prime. So substitute f prime by 8x cubed plus x squared plus 10x minus 22. And then use power rule. Okay, use power rule. Now you increase the power. Power 3, increase power, you get a 4 divided by 4. Don't forget it's constant, the coefficient 8. Now x squared, then what you do is, for x squared, what you do is you increase the power 1, you get x cubed. Okay, x cubed over 3. Now 10x, then what you do is increase power 1 divided by 2 times 10. Now 22, antiderivative is 22x. Now at the end, we plus constant c. Okay, maybe c1 because we already used the c. So finally we get 2x power 4 plus x cubed over 3 plus 5x squared minus 22x plus c1. Now to determine the c1, we use the function value at 1. Okay, so here we know f1, so this is fx. Now f1, plug in 1. 1 to the power 4 plus 1 cubed over 3 plus 5 times 1 squared minus 22 times 1 plus c1. Okay, this should be 2 plus 1/3 plus 5 minus 22 plus c1. So finally this should be 5 minus 20, so it's -15 plus 1/3 plus c1. Now also we know this thing should be 5. F at 1 is 5. So c1 should be 5 plus 15 minus 1/3. Okay, so this will be 20 minus 1/3. So this will be 59 over 3. Okay, So C1 is 59/3. So we can write down. Now we can write down fx. So we get fx. Fx will be 2x power 4 plus x cubed over 3 plus 5x squared minus 22x. Now C1 is plus 59/3. Then we are done. Okay. Okay, example. F prime x is 4 over root square root 1 minus x squared. F1 half is y. Find fx. Okay. First, we use antiderivative. So we know derivative, f derivative. So to solve f, so we should do antiderivative. Okay, antiderivative. So f derivative, fx is antiderivative of its derivative of the constant c. And then we substitute, plug in f prime. So it's 4 over square root 1 minus x squared dx. Now, right now, the only tool we have to do antiderivative is antiderivative table. Okay, so we use antiderivative table. So this will be factor out the coefficient 4. And then use antiderivative table. Now this 1 over square root of 1 minus x squared. Remember, arcsine derivative. Arcsine x its derivative is 1 over square root of 1 minus x squared. Okay, so to do antiderivative, then we get antiderivative of 1 over square root of 1 minus x squared will be its antiderivative table, arcsine x. Once we're done this thing, we plus constant c. So we use the applied antiderivative table. Derivative by antiderivative table. Okay. Now to determine the constant c, then we need a special value. Plug in function value at 1/2. So f1 half will be 4 times arcsine 1/2 plus c. Remember, what is arcsine of 1/2? What is arcsine 1/2? Arcsine 1/2. Sine, what angle is 1/2? Sine pi over 6. Okay, sine pi over 6 is 1/2. Arcsine is the angle to define arcsine is negative pi over 2 to pi over 2. Okay. So it's 4 times pi over 6 plus c, which is 2 pi over 3 plus c. Now we know f at 1, f at 1/2 is 1. So the thing we know, we also know f 1/2 is 1. We also f 1/2 is 1. So we can conclude. That 2 pi over 3 plus constant c should equal to 1. So which means we can solve c 1 minus 2 pi over 3. Okay. And then we can substitute the c back to the expression. So we get, then we can finally now solve fx. Fx should be 4 times arcsine x plus c, which is the 1 minus 2 pi over 3. Okay, then we are done. Okay, another thing is application of this antiderivative. Okay, some applications. We know that in differentiation, we know if we have a velocity, we have position function of some object, then we can find its velocity. Okay, applications. So given suppose that we have a position function s equals st. Suppose that we are given that the position function, the position of an object at t, at time t, is s is a function of t, st. Okay, then it's a velocity. So suppose to make this easier, we suppose that the particle, the object is particle moving on a straight line. Okay, moving on straight line. Then its velocity. Then instantaneous velocity v equals vt is ds over dt, derivative of position function, or you write as prime notation, f prime at t. And the acceleration is the instantaneous change rate of a velocity. So a equals at, acceleration is dv over dt. This is also v prime of t. And this is also, v is first derivative of st. If you take derivative again, okay, so this is actually second derivative at t of the position function. Okay. Now, actually, we can solve from acceleration, solve the velocity, and then from velocity, we can determine the position function. Okay, so if we are giving acceleration, then how do we determine velocity? Okay, now velocity, to determine velocity, then what we do is we just integrate, find antiderivative, okay? Find antiderivative of acceleration. And then from Vt, then we find St, which is antiderivative of velocity, okay? Antiderivative of velocity. Now, a special case in physics is constant acceleration, okay? Constant acceleration. If a special case in physics, if a is constant, at is a constant, equal to a is a constant, then we have Vt is a dt, which would be at plus constant c. Now, if you take Vt to be 0, let t to be 0, then we get V0 to be a times 0 plus c. So this is the a times 0 gives us 0. So this is actually 0 plus c, which is c. So here c is nothing else, i.e. c is the constant c. The physics meaning of this c is initial velocity. C, i.e. c is the initial velocity, the initial velocity, initial velocity. So now if you write initial velocity as v0, okay, suppose it's initial velocity v0, so you can write vt is v0. If you write it, plug in c, so it's at, plug in v0, okay, or v0 plus at. So once we solve the vt, then we can find its position function. Then its position function is antiderivative of vt. Position function is the vt antiderivative. Then we substitute the position function, which is at plus v0. Or it's more conventional to write as v0 plus at, v0 plus at dt. Now, if you distribute, okay, v0 is initial velocity, so it's a constant. So it's a number. So it's a v0 dt plus at dt. A is constant. So v0 is constant, so it's antiderivative v0 times t, okay? Or you factor out v0, let d cancel this integral. Okay, so it's at antiderivative It's very easy to check. T has antiderivative t squared over 2 times a. Once we are done, we plus constant c1, let's use. So we get this is v0 of t plus 1/2 at squared plus c1. Now, if you let t, take t to be 0, plug in t to be 0, t0, the initial, the starting point, S0 will be, the initial position will be v0 times 0 plus 1/2 times a times 0 squared plus c1. So this is 0 plus 0 plus c1. We simply just c1. I.e. c1, the constant c1 is the initial position. Okay, so we can write down this is, so S, so this is C1 initial, S, suppose this is S0. So S equals, then we get V0t plus 1/2 at squared plus S0, okay, plus S0. Now, if you set the initial position as the initial position, i.e., if we set S0 to be 0, we set the initial position as 0, then we have the chain. So here, chain of position, then you get this is displacement. Okay, displacement. The displacement will be the position function because S0 by our choice, we choose to do it to be 0. Okay, so displacement of constant, acceleration motion is v0 times t plus 1/2 at squared. Okay, example. The free fall motion. Now the idea is, so suppose you have an object. Suppose it's a particle of a small ball. Okay. Now at a certain height. Now if you set it free, let it go at a velocity 0. Okay, velocity 0. Initial velocity v0 to be 0. Okay. Now the acceleration. What's the acceleration? Okay, the acceleration will be constant acceleration on the Earth. The acceleration is the gravity constant g. Okay, it's g. The acceleration is 9.8 meter per second squared. Now you need to be careful. This 9.8 is determined by experiment. Because here the Earth is not a perfect ball. Okay, because the Earth is not perfect ball. So the radius is bigger at the equator than at the north and the south pole. Okay, then the constant, the g free fall motion, the constant here is not exactly constant. Okay, it's not exactly constant. So on the equator and on the north pole, south pole, g will be slightly different. But here, for convenience, let's just choose constant g. Okay, on the Earth, the g is determined by the Earth. Okay, so it's 9.8. So on the Earth, the free fall motion will be s. So this will be we choose our initial point to be 0. Okay, So this will be st at time t. So time t here, then st will be 1/2 g squared, gt squared. So v0 to be 0. If you set v0 to be 0, a is g, okay? So the free fall motion is this, okay? Okay. Okay, suppose now suppose we have okay, suppose one object, suppose you throw one object on some building, a tall building. Suppose the tall building is 490 meter. Okay, the tall building is 490 meter tall. Then at the top, on the top, so some object, you know, it is set free, set it free, a small ball. Now let's find the time t, total time t, such that the ball hit the ground. How many? What's the time needed? Okay, 400, 490 meters. Now, so here the initial position here, then the displacement, the total displacement is actually the height of this building, 490. So we're giving s is 490 meter. To find the t, then we need to find, you know, s equals 1/2 gt squared. So at time t, it hit the ground. Okay, so this is the 1/2. If you plug in the constant 490, this will be 1/2 times 9.8 t squared. Okay, then this is the 4.9 t squared. So if you divide by 4.9, then you get t squared 4.9 divided by 4.9, which is t squared. Now this thing, you get it, this thing is 100. So t, you get a t to be 10 seconds. Okay. After 10 seconds, then this object will hit the ground. Okay. You see if a helicopter lost its power. Suppose the height of the helicopter is 490 meters. So the reaction time for the driver is, you know, is 10 seconds. Okay, it only takes 10 seconds to hit the ground. So the reaction time is really small. Okay. Any questions? Okay. Now let me mention a little bit the G. The G is determined by the Earth. 9.8 is determined by the Earth. Now, if you have another planet, if you have another object, another planet, then, for instance, if you were Armstrong and went to the moon, then what's the constant? What's the constant on the moon? The acceleration constant on the moon. You can. It's not difficult to compute. It's around 1/6. It's around, more or less, it's around 1/6 of g. Okay, 1/6 of g. i.e., if you can lift 100-pound object on the Earth, then on the moon you can easily lift 600 pounds of objects. Okay. Another example of this constant acceleration motion. Example. Suppose a stone was dropped off a cliff and hit the ground with a speed of, so suppose a stone was dropped off a cliff and hit the ground with a velocity, with a speed and velocity. Speed is the magnitude of acceleration. For acceleration, usually we have direction, positive, negative. For speed, it's the magnitude. It's always non-negative. So what's the height of this cliff? The question is, what is the height of the cliff? Okay, now suppose this is the cliff. Now a stone was dropped off this cliff. Now it hit the ground. So this is the ground. This is the ground. Now hit the ground. So suppose at T, this T, at T, it hit the ground. Then, okay, suppose a solution. Suppose at T, suppose at time T, the stone hits the ground. Now this is constant acceleration, motion of constant acceleration. So we know V, so this is on the earth. This is on the earth, okay? This is on the earth. So V is Vt is gt, okay? Plus V0. You know, V0 is constant, V0 is zero because it's free fall motion, okay? Dropped off a cliff. Well, the initial velocity is 0. So actually we only have AT. A is constant, G is GT, okay? Now here, so we know this is 120 feet per second. And then G, then you need to change it into meter. So how do we change feet into meter? Change feet into meter? Change feet into meter. Feet into meter. Feet into meter. And then you find this T to be let's use another unit. I don't want to feet. I'm not comfortable with the feet. Let's use 40 meter per second. Let's use 40 meter per second. So it's really here feet. 40 meter per second. So we don't need to change unit anymore. So T should be 40 meter per second over 9.8 meter per second squared. So if this physics, you can use G to be 10. Then this is 4 meters per second. Okay, G is around 10. Use this operation. G is around 10. Okay, 10 meter per second squared. Okay. So T is the thing. So the height of the cliff will be so the total displacement ST. So the height of cliff equals to displacement of the stone. Now at T, the displacement of the stone is 1/2 GT squared. free-fall motion, velocity is 0. So this will be 1/2 times g times t squared. Okay, so it's 1/2 times 9.8 times t is 4 squared. So it's so if you take g to be 10, so we just do a rough estimate. Okay, g to be 10. This is 1/2 times. So it's 16 divided by 2. So it's 8. So it's 80. Okay, so 80 meters. Okay, 80 meters. Okay, the height of the cliff is 80 meters. 80 meters. Okay, we have 5 minutes. Then we will let me give you a remark. Let me give you a remark. When we talk about the derivative, usually we talk about it on an interval. Okay, now you need to be careful. Constant derivative is 0, but if a function has 0 derivative, is the converse true. So if fx derivative is 0, if f derivative is x is 0, is it possible fx is constant c? Okay, so you need to be careful. If this is an interval, then this is true. If this is not interval, okay, then it can be false. Okay, for example, we just do this function. Okay, it's defined, let's more or less like a floor function. You can choose any constant, So here is defined for some a, to some point b. Suppose it's b. So it's defined. Suppose fx is defined. Fx is defined a to b. Subject some intervals, some union. Okay, sorry. E1. Let's use E1. E2. E3, E4. Okay, so it's a union of intervals. E1 to E2, union E2 to E3, union E3 to E4. Then you see each interval is constant. If you differentiate f derivative should be constant, because for each interval, derivative, when you do derivative, it's only determined by the local property. Okay, the derivative is local. So if you do derivative, so locally it's constant. So its derivative is 0. Okay, so it's locally constant. But globally not a constant. Locally constant function. Then you see this function has derivative 0. However, globally the function is not constant. Okay, so it can be locally constant but not globally constant. So this is why when we talk about a derivative, we talk about one interval. Okay, one interval. To be more precise, for instance, when we talk about this example, we write as ln absolute value of x. It has two intervals. Here, 1 over x is not defined. Is undefined. At x equals 0. So it has 2 intervals. So to be more precise, we should write in this manner: ln x plus c1, x less than 0, ln absolute value of x plus c2, x greater than 0. Okay, it has 2 pieces. So we do each piece individually. Okay, piecewise. But here the notation is really ugly if you do this manner. So we just abuse our notation to write it as ln absolute value of x plus c. But you should be really careful when you have a non-connected some intervals. Okay, some intervals which is non-connected. Okay, let me just stop here. I'm gonna continue next time.